So Ross and I have agreed on broken what we've decided is this business has to
Okay, let's kick off. Good afternoon. So welcome to the Computer Science Research as a Seminar. And today I'm very pleased to invite, the Professor Ashby Andrews, Professor of the Distributed System from the University of Leicester, to come to visit us to give this invited talk. And Professor Andrews is also the Director of the Enterprise and Impact at the School of the Computing and Mathematical Sciences at the University of Leicester. He has working on the AI, distributed systems, digital twin for many, many years, and published many papers in the top journal and leading conferences, and also secured a lot of research, the grants funded by the Research UKRI, Innovate UK, EU, and also the leading industries like BT and CGIs. And today, I'm very pleased to have Ashby here to give the talk entitled "Self-Learning Digital Twin for Cyber Physical System." Now, hand it over to Professor Andrews.
Yeah, so thank you, Professor Liu, for inviting me. So, can you hear me, people on the back end, or I can use this one? Okay. Okay, so good. So I have structured my talk in a way that there should be a bit of a background, bit of theoretical developments, and bit of applications towards the end. So depending on your background, so it would be probably interesting to most of audience in one way or another. So I would start with very basics and introduce what is digital twin and what are different taxonomies or classifications of distributed systems. Digital twins, right from kind of simulations to kind of IoT-based kind of developments to more towards the current era where people are talking about physics-based AI-driven digital twins. So I would try to cover that, and then I would go into a little bit more depth and start talking about what are the different kind of ways we could build digital twins. And then towards the end, I will present three different applications. One is in environment, another is in health, and the third is more towards a kind of a distributed autonomous vehicles and then similar kind of things. So all the last three projects that I will be giving are mostly funded through EPSRC, so I would give a brief overview of that. And most likely I will finish within the next 50 minutes, so that there is enough time. Probably most of you are aware what digital twin is, but just to set the context, a digital twin is a replica of any physical system. And this is precisely the physical system that I say cyber-physical system. The difference between a normal physical system and a cyber-physical system is that in cyber-physical system, mostly the digital and the physical sides to some extent meet somewhere in the middle. So any physical system that has a sensors attached, or that has to some extent a kind of having the ability to learn or generate data actually, so we would say it's a physical system or a cyber-physical system here. So, and the digital twin is to some extent a virtual representation, or in other words, a replica of cyber-physical system. And it mostly relies on the two aspects. One is the data, and a lot of digital twins people are building or implementing are based on just simple the data aspects. And there is another community, especially people from mathematics and physics aspects. They're talking about more a mathematical or a kind of modeling view of digital twins. And then there is a third community who thinks that both things somehow need to be assimilated into a single model. So whatever end goal is, whatever the approach is, end goal is to have as a real representation or a replica of a physical object, and that to some extent learns as the physical object is changing. So the digital twin is to some extent not a static copy of an object. Rather, as the object is changing or evolving, theoretically digital twins should be changing as well. So now, having said that, digital twins lets us understand what is the current configuration or operational capabilities of cyber-physical systems are, but they also help us to predict the future as well. So in a way, they will help us that how this particular object or this particular cyber-physical system will be behaving in future. To some extent here, people may be questioning or thinking that, by the way, at a limited scale, AI is doing the same thing as well. Based on the past observation, we could to some extent predict the future. But here in a digital twin, it's attached to a physical object. And as the object is changing, object mean it could be a machine or it could be any kind of system that is physics attached to that. So then when that physical object is changing, so we need to some extent learn that object in the changes in that object more or less in real time, and then see that adapted all the time to see that we are presenting a realistic replica of the objects that is in an operation. And then the most important thing is that digital twins should behave as real machines. So because people otherwise would not trust them, people would not have a kind of a right level of trust if what digital twins are presenting versus how the actual physical object or cyber-physical system is to some extent behaving or operating. So as the machine or physical object or cyber-physical system is changing, so digital twins should be able to accurately capture and represent the functionality almost in real time. So that's to some extent a broader view of a digital twin is. Now, just another background slide. So some people, especially modeling community or simulation community, so they have a question that, oh, by the way, we could capture physics in an existing simulation model, and then we could have a realistic state estimation of how a physical object is changing. So here, the difference between a normal simulation and a digital twin is that, so we could design objects or physical systems in a digital twin, then once they are built or kind of operationalized, and when we are kind of capturing the key parameters, we could almost within the same environment learn from them and could improve the design as well. So it's essentially, it's three important things. So right from design to a kind of manufacturing or implementation or prototyping to when that prototype is in operation, we could connect the loop or we could close the loop actually. So here all planning to operations, all things we could test and deploy in a digital twin. So for example, we used to work closely with Rolls-Royce. Previously, Rolls-Royce used to have simulations. Based on those simulations, they would be creating a prototype, and when that prototype goes into production, and once they measure the key parameters, they would say, oh, by the way, what we designed and what is in operations, probably they cannot synchronize. So but with the digital twins, they could check the parameters when something has been operationalized, so that we could connect the loop actually. So, and obviously it's a combination of all that historical data, simulations, and then obviously human knowledge as well. Digital twins are very application specific, so you would hardly see anything that's very generalized. Rather, they're just tailored to individual application needs. So, and the most important thing, it's not just the kind of design and prototyping, it's also the lifetime aspects as well. For example, the warranty issues and how the object would change under different kind of environments. And so, and all the processes and systems we could embed right into the digital twin as well. So, and obviously there are different applications, right from optimization and in cost and quality of service and any aspects that we could develop within a digital twin. So, but whenever we are working on a digital twin, so we have 7 to 8 different projects with different either through funding agencies or start from the end goal, and then we have to go back to that how we are going to do that as well. So most of the time people come with the end goal, so that, by the way, how can we go beyond current AI systems? What digital twins can offer that we cannot kind of see or implement? And then what's the difference between AI and a digital twin, and what's the difference between a simulation and digital twins? So some of those questions I would be trying to answer in the next few minutes actually. So another aspect is that people, they say is that what's the difference between a digital model and a digital shadow and digital twin? So if you talk to an environmentalist who is doing a kind of building information modeling, BIM for example, this is that, by the way, we are trying to do similar kind of things. So we could create a kind of ontological view that's of all the sensors data that we are collecting from buildings and create a model. So if the person is coming from, for example, another thing, for example, health, they say that we have been doing UMLS or a similar kind of ontological modeling. So what the people say as ontology, then to some extent this is also to some extent digital twin as well. So and this is a reason. So this is a kind of a bookish definition that's is commonly available in literature, is that the digital model, to some extent, when we have digital model of a physical object, to some extent we have a kind of a manual interactions where, for example, this could be an ontology, this could be a BIM model. So we are physically a kind of entering and we are trying to map the physical and digital objects. So, but it's very hard to simply change the digital object to inform the physical object to change its configurations. Probably that's not possible. So, whereas in a digital twin, it's to some extent it's bidirectional. It's to some extent bidirectional synchronization. So we learn from a digital object, and the digital twin should ideally be a kind of propagating or informing the design of the underlying physical system, or if design cannot change, obviously something is in operation, then at least the optimal configuration of an object that's in operation. So that's kind of ideal definition. Now, implementations could be obviously very different. People from application to application, for example, this would be very hard to implement in a healthcare project. If you are trying to create a digital twin of a lung or a heart, then probably this would be subject to a lot of ethical and other regulatory um, um, kind of compliance, but this is where basically the whole research is going, so that a digital and physical objects should be asynchronized, both in terms of the data as well as underlying physics or processes as practically it's possible. So now this is one aspect. Now there is another aspect as well. So if you have to create a digital twin of this particular machine, this is a Rolls-Royce engine, so although it looks like one machine, but behind it, there are thousands of components, probably in some cases it could become millions of components if we bring everything together actually. So now, interestingly, they may be generating data. So for example, on one plane, there are 15,000 sensors. So you're, so on wing of a particular, for example, Airbus, there are 15,000 sensors. And overall, there are hundreds of thousands of sensors that are deployed. But most importantly, if you have to create a digital twin, it's not just the sensor that's important here as well. So it's the physics that's also equally important, because if this object is in operation, at each moment its physics is changing. So to have a realistic replica of this object, so we not only need to capture the data, we also need to capture the physics. And physics is to some extent changes because this object is undergoing extreme pressure, heat, and a lot of changes while in operation. So it means that although the data that we are getting to some extent may be a realistic representation, but data is to some extent, this is not continuous. Data is giving us at probably every second or minute or X number of times per hour. So especially this object is in the air, we cannot try to monitor it almost in real time. So each component has its own physics, and this is and that physics is not static. The physics is changing. Number one. The number two is that this physics is not working in isolation. Rather, this is an interconnection of different physics objects. So it means that an individual object may not be changing as its physics stands, but a physics or another physical changes in other objects may have influence on the operation of this entire machine actually. So here we have to think of three things then. Number one, what is the data that we are receiving? Number two, what is the individual physics in ideal world, and the physics that's evolving due to the operational constraints. And number three is that then how, as a whole kind of system, when we put together, how different individual components influence the design or influence the operations of the whole machine actually. So, and if we have to create a digital twin, so we need to basically, number one, have all the data, and data could be through sensors and other means. Number two is the physics of that. Number three, that what's the exact flow of that physics, and to some extent the workflow of that. And then this is not a constant, this is changing all the time. So what should be the right configuration that, that we should be using, and then how we should be able to do that? The object that is up either in operation or in production versus the digital twins that we have on our computers to some extent synchronized. So this is quite a challenging undertaking to have this kind of functionality, because there are aspects of modeling, there are aspects of algorithms, there are aspects of computational complexity, and there are aspects of, to some extent, communication and networking that we need to have in a single digital twin. So that is another challenge that I wanted to see when you build kind of large-scale digital twins. So that's to some extent a distributed system of thousands of components that have its own physics and data, and they need to be orchestrated in a particular way so that the overall message is compliant with the wider physics models that the mechanical engineers or the domain experts that have established. Now, having said that, digital twin is not a new concept. So if you look at the first mission that landed on the moon, Apollo, so the digital twin started from that actually. So it was to some extent 80s where people started building digital twins actually. So people had that 3D modeling, this remote programming, and all those aspects. So, but it was absolutely a physics-based model. So a physics that every component had a physics, and it was very compute intensive and resource intensive kind of undertaking. Then probably 15, 20 years later, people started talking about that how can we print more as the similar kind of objects. For example, if you have a CAD-CAM model and you want to print that, people started talking about 3D printing and virtual assembly and the connection between how we productionize it and how we design it. And then people said that, oh, by the way, this is also a digital design, and then we could say it's a digital twin. So, but it was absolutely a physics-based model, actually. So it was very difficult to learn from objects that's there, reconstruct the physics, and to ideally inform the model in reverse engineered way. So, and then there was another big thing. So IoT, so there are 50 billion, or people are saying up to 2 trillion kind of devices that are there in production. So, and people started collecting a lot of data. And this is where BIM and all those became mainstream, and IoT and monitoring and streaming and all those kind of microservices and to some extent became quite prevalent, actually. So here people started thinking that, by the way, what people were trying to do here through physics, to some extent we can do through data as well. But again, the question arises that how accurate is the data, and if there are gaps in this data, and if there are kind of fault issues, then obviously data itself will not be able to handle that. And then another kind of mainstream thing that became kind of again prevalent was a lot of gaming engines started coming. Probably you know that Unity and Unreal. So people can create kind of different objects in gaming engines. And these gaming engines to some extent also has physics as well. And then you could virtualize and to some extent create any particular hypothetical scenario, and you could instantiate in a virtual reality and augmented reality. So virtual reality was obviously the visualization, and augmented reality was to some extent capturing the environment and bringing that into your design as well. So, and then here obviously started thinking, when we built almost 10 years back our first digital twin, so that was to some extent a kind of AR, VR based actually. So what we were doing is we were trying to automate the CAD-CAM models into a machine learning environment, and then try to see that how can we overlay AR, VR to kind of update the model as objects are changing. But there was no physics kind of attached to that. So, because it was very difficult to have a kind of a physical representation or physics-based model behind an AR, VR-based model, because if you could get closer to physics, then you would have a motion sickness, for example. So, because with CAD-CAM, you could only have 1 or 2 frames per second, whereas in ideal AR, VR, you need 100 frames per second to have realistic kind of experience. Otherwise, you would feel uncomfortable from your experience. So, and that's the reason here people started talking about that we need to bring data and models together, because otherwise, all those environments, there's ideal, they're doing the things, but either they're very expensive or they're not very realistic. So how can we have realistic, but at the same time, a cost-effective ways to build digital twins that are to some extent also getting benefit of the modern AI-based developments, but also they are closer to physics-informed models as well, actually. So, and here people started talking about accurate and real-time models, self-adaptive capability, automated synchronization, and this is where we started that it should have physics, it should have obviously learning and data together, and then it should be doing more or less the same things people were doing here as well. And this is where we are now actually. So in last 2 or 3 years, there has been a lot of development. Mostly probably you would have seen in EPSRC or UKRI, there has been bulk of the investments in this particular area. They have funded a lot of projects, but probably they were looking something in that area. We were fortunate to have 3 projects in EPSRC in that particular domain as well. So Now, another thing that changed the whole kind of landscape was the kind of emerging of new applications. So probably you're most of the time aware of what's happening here, either those are surgeries or robotic kind of operations or aerospace or automated manufacturing, surveillance or self-driving cars. So if we have to create a digital twin, so obviously we need an AI model. That AI model is not just relying on simple data streams. Rather, we need to build something that could be governed mathematically and should also comply with physics laws as well. So if I have to create a digital twin of any of those things, so I have to some extent comply with this statement, so that I should not just simply say that I'm learning from data because data could be faulty. Data could not be synchronized with underlying physics. Data could be, there could be errors in sensors or other aspects as well. So as a result, we should be able to kind of learn something that's not realistic of what's going on in a machine actually. So it means that as we are moving along, so both mathematically and both in terms of physics laws, we need to capture those capabilities and embed that into AI models. And then, interestingly, the AI models need to learn at the scale of the machine's operations. And that the most interesting thing is that most of the machines are a continuous machine because the physics is to some extent a continuous function. It's changing all the time and it's learning all the time actually. So, and that's to some extent the challenge that the future digital twin are kind of posing upon us. And if we have to have a realistic digital twins, then we have to have kind of these capabilities embedded in our digital systems. Now, going forward, broadly speaking, the models in digital twins we could classify into two again branches. So, and here most of the people were to some extent and historically, this is what the physics-based models are. So they were physics-based models. And here, to some extent, are mostly machine learning-based approaches. So machine learning approaches can kind of be appreciated for their performance, their scalability, learning to some extent, kind of unknown parameters, and having the capability, both in terms of performance and scalability, that did not exist. On the other hand, what was missing was, to some extent, trustworthiness and the reliability, because you cannot control the behavior of machine learning models. You cannot understand what's the provenance of the learning is, or what you have learned from underlying data, because to some extent, most of the machine learning models are black box models, actually. So now, can we ideally have a digital twin that to some extent get benefits of the two schools of thought into a single kind of system? So this is one aspect that was challenging us. And even interestingly, so if you have a kind of cyber physical system, so just on the top left, okay, sorry. Okay, so there are two extremes. So one is if you have you're just relying on data. So on top left corner, or the versus on this side. So if there is a lot of physics, most likely there would be no data. And if there is a big data, there would be no physics. So if you have to have a reliable system, you need to have both some data and some physics. And that's to some extent fundamental for any digital twin or any reliable replica of a cyber physical system. And that's the big problem there. Because most of the AI projects are on the right-hand side here. And most of the simulations are on some extent on the left-hand side as well. How can we, to some extent, operate in the middle so that, because you need to understand physics to even rely on your data as well. And you need data to understand how your physics is operating. So if we don't have any of those, whatever we would propose there would be questions. Now, how can we bring those things together in a single system that is to some extent consistent with physics laws? And then we could also empirically validate through the data that we are getting as well. And this is basically the key questions that's coming when you are building the digital twin as well. And now here, so for example, in an environmental observations, most of weather forecasting, for example, you could predict a state. But then also you could analyze data and predict another state as well. So if the two states don't synchronize, then which state to kind of rely on or trust actually? And that's to some extent a challenge actually. Now by bringing both models and data together in some way, so we would be able to predict the states that to some extent could be validated in a way that individually was not possible. So for example, either we could be closer to data, or we could be close to a model, but realistically, somewhere we need to sit in between actually, and that is to some extent the benefit that we are saying that if we could have a physics-informed machine learning, physics-informed machine learning is that that is learning from data, but it's at some point in time in their learning capability, at different point in the whole workflow, we need to embed physics in the overall kind of workflow. Now, how can we do that? So here we could do it at 3 different levels. Either we have to do it at observational level, or we could do through inductive biasing, or we could have a learning bias. So, and when we say physics-informed models, obviously the models need to some extent operate at different level. So for example, operational biases. Remember, one thing that you could do is you could use physics to test the correctness or validate the authenticity of the data itself as well. So for example, if you're getting streams of data, can you validate that they are adhering with the physics laws as well? I will be showing you one slide later. So where we are trying to get data from real sensors, and we says that by the certain points during the night time, if we are capturing NEE or carbon dioxide, for example, so during the night time, the sensor is not operating correctly. So how can we embed physics laws to see that which data is right and which data is not right actually? So observational bias is an important aspect that we need to kind of understand and cater for. The second thing is that inductive bias. During the learning, if we could embed that mathematical capability, and to some extent, we could say this is the prior learning. If we could incorporate that prior learning that's coming through mathematical principles or simulation models into a kind of at the right level, so we could enforce the predictions to implicitly satisfy certain physics laws. So that, for example, if the data is going in right and left, or if the learning is doing that's kind of violating physics laws, so we could simply kind of ignore that and rather force the learning functions to follow a kind of path that fulfills the physics laws. And the third is essentially we could do it architecturally, where we could again here kind of tweak the models mathematically so that either our inferencing or the learning itself in a machine learning model should be subject to a mathematical functions actually. So these three things obviously we need to be aware of when we are trying to create a physics-informed models that are informing the underlying kind of learning capabilities of a digital twin. Now obviously, I'm not talking about the computational complexity. I'm not talking about the cost when we bring everything together. Obviously, it would be obviously we would be when we are trying to kind of address that bias, the more kind of we remove the bias, we are adding additional level of complexity. So, but we will discuss later that what's the computational cost of embedding that particular capability in a model. Now, so there are three ways we could embed physics, or we could work within a physics as well, and that's, by the way, pretty kind of common three ways that I would be explaining. So one is that we could use prediction from machine learning and physics-based models to see that what's the uncertainty. To some extent, if both physics and machine learning model are telling the same story, that we don't need to worry. To some extent, we could say that, broadly speaking, they are together. If, for example, if we could say that our threshold is X%, and if we are within X% of accuracy, we could see that, depending on the applications, we could say that that we are adhering to a certain physics-based principle as well. But again, if we're doing a real-time system, that will not be possible as well. So it could be more kind of in a certain scenarios where there is a lot of simulation data, and then we are trying to learn to some extent from this. That could be a possibility that we could learn few scenarios. So, and especially if we are doing more kind of forward designing, for example, physics experiments at CERN, they have been using some of that approach to validate or design their systems. Now, there is another aspect, and this is the most important aspect. This is where most of the time we are operating these days as well. So we can integrate physics laws into the machine learning training process to simply force the machine learning to learn in a much more controlled way. And that is where the bulk of the physics informed machine learning is coming. And probably there is a lot of research going on for different applications, depending on the nature of the physics and the amount of data that we have. So here the physics equation, to some extent, moderates the learning process, and the learning needs to comply with the physics or the mathematical principles as well. And the third important thing is that more kind of, this is where we are heading towards generative aspects as well. So people are generating data, but if you look at the generative capabilities, so they are not mathematical oriented. They don't rely on the mathematical principle as well. So how can we embed a mathematical or physics laws into the generative kind of AI so that we could still generate the future data sets, and obviously from those data sets we learn, but most importantly, what we learn or what we generate has strong mathematical foundations. Otherwise, if we are learning from 1 million objects, but still if there is no kind of mathematical or physics principle behind it, to some extent it's a wild guess. But on the other hand, we probably, people still have more trust on established physics and laws than they have to some extent on the black box models as well. So if we can simply generate a data that's based on certain physics and mathematical laws, and then we could learn from that, at least we know that we are learning from the data, and if we know the data distributions, we know that from where the learning came actually. So these are the three things, depending on the nature of the applications in digital twins, we could do that. And now here, so there are the three benefits that we could have. We could solve, to some extent, both supervised and learning tasks while respecting physics laws. We know that if we are kind of providing a solution, that solution is not learning from the black box capability, that there is a physics or mathematical law behind it. Most importantly, there is another domain coming as well. So sometimes you may not have a physical process or mathematical principle attached, but you could learn the mathematical function from your data actually. And this is this data-driven discovery of PD, so you could learn new physics as well if you are having a kind of trillions of data streams, and you want to see that, okay, how some object is behaving. So it's not that you explicitly embed a mathematical object or physics law into the learning function. It could be other way around as well, that you could train your model to learn an equation, and then equations obviously could be further validated as well. And the third thing is that you could remove unrealistic solutions that violate mathematical laws actually, even if, for example, your data may be telling a different picture, but if it's violating mathematical laws or some fundamental physics laws or biological laws or chemical laws, people would have a lot of questioning before they could trust the outcomes of a particular system actually. So now the question is, okay, if you have both a data and a physics, so who should you trusting more? So here, so there are two aspects as well. So to make things simpler, we didn't go that extreme where we say that we would replace data with physics. We are saying that both could coexist in a single system, actually. So part of the functionality could be coming from physics, and part of the functionality could be coming from data. We would give weights. And here, an ideal case, if you, and by the way, this is a matter of computational complexity. So if there are gaps, you could trust physics. If number one thing, and that would be the least compute intensive or complex system. But if you want to test each and every step of learning through a mathematical physics-based principle, then you are adding a layer of a kind of trust, but that trust is coming at a cost, and this is seen with computational complexity as well. So it's more kind of, this is a system a kind of decision than to anything more technical issue, actually. So obviously, depending on the granularity or the complexity, or to some extent sensitivity of your applications, you could configure those things and put weights that in an ideal world, so every physics laws is, and each step is being tested by data, and every data is to some extent subject to physics principles, but that would be extremely compute intensive because you're doubling the computational cost of that as well. So what we are aiming to do, or what we have achieved as well, so for data we have to some extent a data encoder, and to some extent the same about the physics as well, but there's a joint or a common decoder, and from decoder we could reconstruct the data. So here, it's to some extent we are relying on the data, filling the gap through physics encoders, and to some extent having a common latent space, and then that latent space is to some extent either directly fed into machine learning models, or we are producing the data that probably downstream applications will use it as well. So, we just kind of submitted a paper in ICLR, and that's to some extent the approach that has gone into that as well. So, now, that was to some extent that what are the potentially people in terms of the approaches that are using. So now, what are some of the applications that are benefiting from? This is one of the projects that we are doing. So I would be spending next 5 minutes to explain different aspects of that. So, so this is our EPSRC project. We say self-learning digital twin for sustainable land management. So, and this was one of the projects that was funded in the AI for Net Zero call. So probably you know that. Through Earth observation models, we have a lot of satellite data. So there is a lot of sensors deployed. There's a lot of socioeconomic data, and obviously there are a lot of computational models. By combination of those, we could create a digital twin. Here, obviously, the end goal is to create a digital twin of Earth. But what we are trying to do is we are trying to create just a digital twin of a UK land management for 2 regions, mostly in East Anglia. And the 2 sectors that we are considering are ruminants and peatlands. And those ruminants and peatlands collectively produce 12% of the UK emissions, and ideas that how can we reduce those things. So we are working with a lot of kind of organizations, and just I would be explaining that what we are trying to do here probably in the next slide here. So here you could see that simulations are coming through with JUICE. JUICE is a joint UK land environment simulator. Metafis has been working on this for the last 2 or 3 decades actually, and there's a huge science and community behind it. So here we can produce kind of a digital twin of a particular location, and if you say that historically what type of crops they have been growing, what's the physics of individual crops, what data we have, and what has been the overall weather patterns. And the weather pattern has been coming from Center for Ecology and Hydrology, both in terms of the soil moisture, and then obviously the daily kind of geological data as well. So we feed everything into a simulator, and then obviously this is one aspect. So because this is giving us to some extent the physics, then we are also getting a lot of data from Earth observation as well. So Leicester is as a very famous National Space Center, and we have a space park. So almost all the space companies are around us. So we have petabytes of data that's available. So what we could do is we could any longitude and latitude we could have historical data to see that what crops has been grown on that, based on that we could see that what has been the net eco exchange, and we'll be explaining in the next slide. So essentially, net eco exchange is how much carbon is being absorbed and how much carbon is being emitted. The difference between the two is, we say, it's a net ecosystem exchange, and this is what people are more interested. So when we say that, by the way, this is to some extent red area, it means that the production of carbon dioxide is more. Whereas other sites, if there is much more greenery and biodiversity, then obviously it would be a net sink. So practically, we can go into any area and we could tell that basically. So, for example, this is one area where you could see here. So we could say that how would a heat wave affect the greenhouse gas balance in a particular location, for example, and how would loss income from crops be offset by carbon credits? So, for example, if you are asking a farmer to basically replace this crop with another crop. So, but they would be asking, by the way, government need to incentivize, because if we are trying to generate less carbon, then obviously maybe we are losing income as well. So it would be less attractive to farmers. So, and it's more to policy interventions that government need to do as well. So similarly, what's the impact of different crops on the greenhouse gas balance? Because the government wants to know that which crops are to some extent both economically feasible and at the same time environmentally friendly as well. So, and these are some of the questions obviously our digital twins would be able to answer. But if we try to answer this question based on the data, probably people will not trust. But if there is a science behind it, if we could say that, by the way, there is a physics models, this is mathematically verified, we could provide you the whole provenance, and digital twin is giving the answers within this certain level of kind of uncertainty. And if we could quantify the uncertainty as well, people would be able to trust that as well. So, and this is some extent the main focus of this particular project that we are having. So, for example, here, I give you an example. So this is a particular sensor that's to some extent measuring a kind of net ecosystem exchange in a particular site in East Anglia. This is now the problem is, during the day, most of the readings or observations that we are collecting from these sensors. By the way, there are hundreds of those sensors at different places. So they are within a certain degree of accuracy. But during night time, so what they measure, and especially if the wind direction or if the weather patterns change, so they're not accurate. So now, how can we overcome the problems or the gaps in this particular area? So where, if we are trying to learn something from this data, most likely we will be predicting something that's not accurate actually. So here, and one of the slides I will show that how can we use even physics to validate the accuracy of the data that we are generating, because if there are simulation models or mathematical principles that are telling that how basically during the day and night the NEE should be measured. But our sensor is not telling the same thing. So one of the papers that we are trying to produce. So this is the paper that we just submitted into ICLR actually. So here, this is what we did was, so here we have basically a daily, a weekly, a monthly, and a quarterly kind of NEE emissions. We give estimates. So and here. So to some extent, if you could see that probably sorry, this due to space, this is a bit you may not be able to see the exact. So here you could see that what is the actual data telling and what the digital twin is telling. So there is not much difference. So here, for example, we have trained 4 models. One is a physics-informed model. One is a normal autoencoder model. One is the state-of-the-art that people, so mostly on regression models. So here we have created both a weekly, a monthly, and quarterly, and then we could predict mostly a year ahead, that after a year, so for example, how the data would look like. So by the way, I'm happy to share, if someone is more interested in reading this paper, I'm happy to share the whole draft as well, by the way. So here, we have able to improve the whole accuracy of even the data kind of quality of the whole generation process up to 22%. And then we tested with the actual kind of environmentalist, and they were very impressed that we have done something that was not possible. And that's to some extent we say it's a gap filling. Gap filling is coming through physics informed neural network that we have built, but that neural networks is kind of embedding the partial differential equations that we have simply imported from the Jules model, and that has been, people have been simulating that for almost decades. Now we have embedded that into the neural network functions, and then kind of did the predictions that are to some extent much kind of accurate, and obviously much more robust as well. And obviously, this is our initial intervention. Still, we have a large team, almost 12 postdoctoral fellows who are kind of exploring different aspects as well, and more kind of observations will be coming. But most important thing is here, we don't have used for the time being Earth observation. So essentially, we don't have satellite images. So the next stage is that how can we embed satellite images on top of that to see that what we are telling in terms of our predictions versus what we are getting from the sensors, and versus what the satellites are telling actually. If three things to some extent are kind of synchronized within a certain degree of uncertainty, so we are aiming to go for the next COP to present our results that we could give kind of confidence and at a scale that probably was not possible before actually. So for example here, these are the three particular slides. So now here, this is to some extent nature. Fan is in an East Anglia, obviously, mostly in peatlands. So this is to some extent a net sink. So there is, and although this looks kind of another similar kind of location, but this is another census, but this is a net source of carbon, and this looks green, but actually this is producing a considerable a kind of carbon dioxide, actually, carbon emissions. So because obviously the crop itself, people say that it's green, but they are a huge source of carbons. And it depends, obviously, on the fertilizers, on the soil moisture, and obviously other aspects as well. So, and the simulations captures all those things, and obviously the sensors also captures those. It's the net kind of reflected effect of the production. Now, one thing that still we have not been able to do is to just apportionize that what bits is coming from the crop itself, what is the effect of the environmental factors, and what's basically the impact of soil and all that. So still we have to incorporate that aspects in the digital twin actually. So now, going forward, another aspect that we need to do is, we can, at a certain point in time, we could capture a realistically accurate representation of a state of an object. But can we do it in real time? Okay. So, and this is one thing. Previously, what I was saying is, to some extent, that was static snapshots over a period of time. You could do it a couple of times a day, or X number of times a day. But if you have to regularly do that, then it means that you need to do something in a way that it's to some extent a real-time learning. And if, for example, if a machine or just environment is working around the clock, a digital twin should be able to capture most of those states as the underlying physical object is changing actually. So, and it means that starting either from a learning or starting from a simulation and gradually bringing those things together. Because if you try to do it immediately at this point in time at the start, the computational cost would be quite high. So you may be able to see that what's the uncertainty by 1 or 2 seconds, but this is eventually where we want to go actually. So as the real-time data is coming, if you're throwing that real-time data into a computational model, I mean, with few iterations you could get closer. But obviously it's easier than getting implemented because it's a huge computational cost. Even if you have to kind of identify the boundary conditions of or parameters of machine learning models or boundary conditions of a partial differential equations out of many those possibilities. That's to some extent again kind of either you need to learn or you need to simulate. So, and depending on the right configurations. So it means that the performance is a challenge. For example, here in this another particular project that I will tell you next slide later. So here, so for example, if you have for example, a tumor, for example, and if someone has a tumor and the tumor obviously has certain physics, so there are physics laws that are behind tumors. And now, if we're getting real scans, to some extent, one aspect, and then people are giving different interventions as well. So can we mathematically tell that or embed that mathematical capability within the digital twin to see that what would be the trajectory of a particular disease if we do certain intervention or if we don't do certain interventions as well. So this is one aspect, and on a similar kind of things. So here, although not exactly this, but Professor Luliu and I have a project which is self-learning ability to accelerate clinical care in emergency admissions. So what we are trying to do here is well that if, for example, we have a lot of different data sets, and first we need to learn from that data, and the second thing is that each lung has its own physics. Okay, so and obviously that how air flows within that. I mean, how the air is consumed actually, and then as kind of a function of that, then obviously our lung behaves in different ways actually. So if we bring this data and physics model, and then the conditions that we're looking here in this projects are the two conditions, mostly pneumonia and asthma, because especially most of the hospital admissions during summer or due to COVID, obviously, or due to those two conditions as well. So then the challenge was that can we realistically tell that which are the 20% patients that should be admitted, or which are the 20% patients that should be discharged with a certain degree of confidence? Because if we could do that, probably this would be a big service to the hospitals, because those 20% mostly are taking 80% of the total hospital facilities as well as. So this is another project that we are trying to do. We are still trying to kind of come up with a particular approach. We have identified what type of physics models are and how the lung behaves. We have also access to thousands of scans. We have also access to biomedical data. So we are bringing that together as well. So we hope that we would be able to exactly the same thing. So we don't have a demonstrator. We are probably 3 to 4 months still behind schedule, and we are able to write a paper on this one as well. We have initial drafts. So, but this is where we are heading to as well. So this is MVP SLC project that we started probably a year back, and we are halfway through. We are working with actually the clinical community and with the real data as well. And obviously there are ethical reasons, and that's the reason that slows us down as well. So, and other kind of projects that's obviously very different to the previous two projects that I discussed as well. So here you could see from the applications that to some extent that's collective behavior, network behavior, distributed systems. So here, how individual objects can learn from other objects, keeping in mind the individual physics and the data, but it's more to some extent a collective learning. So here, how can we bring both data and models together in a single plane so that the collective learning that we do should be a combination of the two individual learnings as well. So sorry, conscious of the time, so I'm already closing up to 3 o'clock. So, but this paper is available, so if you need to read this paper, so all those details are within that. So, and by the way, we have another project, similar kind of project that we are doing with British Telecom. So I will not be able to explain what it's building on to some extent. The same principles. If instead of these shifts, if we replace these shifts with individual routers and switches, to some extent each router and switch has its own physics. They are also to some extent generating data as well, and we could to some extent create a graph topology, and there is orchestration, how we will do it. Then we would be able to build different scenarios either based on quality of service or based on cost or based on topological analysis and other aspects as well. Probably my last slide, so we to some extent are bringing physics, but physics is posing a different challenge as well, because if we to some extent are synchronizing physics and digital twins together, what